This video is about comparators, in particular rail-to-rail comparators, and it corresponds to section 33.1 of the textbook. What is a comparator? Well, you can get a pretty good idea of what a comparator is just from looking at its symbol. Amplifier symbol, plus and minus input. That's the symbol we use for a differential amplifier. A comparator is just a differential amplifier, but it's different from the op-amps. And the differences are both internal in how it's designed and in how we use it. The op-amps are used in feedback circuits and are designed to be always linear in the output, so the output is proportional to the difference between the inputs. The comparator is used without feedback. If we look at the output voltage versus the differential input voltage, we get a different curve. It is low when the positive voltage, positive input is less than the negative input, and it's high when the positive input is greater than the negative input. And basically what we're doing is we're converting the analog signal, V plus minus V minus, into a digital signal, high or low. And like all digital signals, we want it to be only high, only low, not to be in any intermediate value. So the idea of the comparator is to make a very rapid transition between the low and the high values in either direction. And that's different from what we did with the op-amps. The op-amps are designed with an internal low-pass filter so that when you put into feedback circuits we don't get oscillation and other unstable behavior. The comparator does not have those internal limitations. It doesn't have the internal slew rate limitations. It doesn't have the internal low-pass filtering, so that the comparator makes its transition as fast as possible given the technology. Well, how fast does it make its transition, and what determines that? Basically, what we have internal to the rail-to-rail comparators is a circuit you're familiar with. A P-FET and an N-FET. This is a standard CMOS output stage. And this power supply usually here is labeled VDD. Okay, so what we've got, if we're driving a capacitive load out here, and that's usually what we have to worry about when we're worrying about how fast something's going to make its transition, is that we have to worry about, well, how much is the resistance for the P-FET and how much is the resistance for the N-FET. And with those on resistances, we could determine what the RC time constant is. We have to be a little bit careful here because when people are talking about the rise and fall time of a signal, they're talking about going from 10% to 90% of the full swing. And that means that the time it takes to do that, if we're looking at it in terms of RC time constants, is, we're going to have e to the minus t over RC, e to the minus t over RC, is 0.1 or 0.9. So what we're looking at is the rise or fall time here. This would be a rise time since we're going up. Would be log of that 0.9 over 0.1 times RC, which is about 2.2 RC. So we're proportional to the RC time constant, but the rise time or the fall time is about 2.2 time constants. So where do we get the rise and fall time from? It's obviously going to depend on the exact comparator we're using, so we have to go to the data sheet or we have to measure it. Let's take a look at what we can find on the data sheet for estimating the rise time, the fall time, or the R-on values. And the datasheet here is for TLC 3702, which is the rail-to-rail comparator that we use in the class usually. And the numbers that we're interested in here are the two lines here at the bottom, the rise time and the fall time. And you can see that the specs here are for VDD is 5 volts, that's up near the top. That's the power supply voltage. We've got a load capacitance of 50 picofarads, which is fairly small actually. It's the sort of load capacitance you would get if you're driving sort of ordinary logic gates sitting around. It's not big enough for big power field effect transistor where we might have a much larger gate capacitance as our load on the comparator. There's another value here which is the overdrive. That's actually how big is that differential input into the comparator. So if it was 0 volts, 0 volts is where it's supposed to switch. 50 millivolts means, okay, I'm clearly well past the point where I'm supposed to be switching. And here they give the rise and fall times as 125 nanoseconds and 50 nanoseconds. And those are pretty good numbers for what we're looking at here, driving a small capacitance. There's some other stuff up here at the top, the propagation delay. This is internal delay, not attributed just to the output stage, the CMOS output stage that we were looking at, but due to the internal circuitry that's trying to decide which one of these things, the amplification that actually makes its mind up. And when we've got a very small overdrive, so a small input signal, it takes longer for it to make up its mind. And you can see at the top here, we can get like 4.5 nanoseconds for a low to high level output transition. So it can take quite a while before it decides, hey, it's changed, I better make that output change. If you've got a much larger overdrive, it takes less time to make its mind. But even an overdrive of 40 millivolts, which is fairly substantial, it still takes 1.1 microseconds for it to make up its mind to make the change, which is putting some limitations on how often we can switch the comparator. It doesn't put much limitation on how fast the transition happens, but if you have to wait that long before a transition occurs, then you can't switch very frequently. So that puts a limitation on the comparator that can be important in some applications. We wouldn't be able to use this thing to do a 10 megahertz sort of signal because it takes microseconds before it makes up its mind to make the change. Okay, this is one way of getting a rise and fall time, is just look it up on the datasheet and see what it says. But it only tells us for one particular capacitance value, and that may not give us a good estimate for other capacitance values because we haven't looked at all what the resistances are. So let's look a little further down on the datasheet here, and maybe it'd be better scroll a little faster. And if we get down here to figure 13, this gives us the high-level output voltage versus the high-level output current. Okay, high level, that means we're trying to drive the thing high. This is the PFET internal to the thing. We're looking at the R-on, essentially, of that PFET. And if you look at the 5-volt curve here for the 5-volt power supply, it's pretty much a straight line. And for the 10-volt and 16, this is even straighter. And that means that we're looking essentially at the on resistance of the transistor there. When you get down to only 3-volt power supply, we start to see saturation on the current. The current doesn't go up, keep going up with the voltage, or it doesn't go up as fast anymore. So we get saturation there. But 5 volts, we're still running mostly in the linear region, at least up to about 12.5 milliamps. So we can estimate the on resistance just by taking the voltage drop across that PFET, divided by the current through the PFET. And so if we look at 10 milliamps, make division easy, looks like it's about 650 millivolts there. So 650 millivolts divided by 10 milliamps, that's about 65 ohm R-on for the PFET. And if we scroll down just a tiny bit further here, we can look at the low-level output voltage versus the low-level output current. So now we're looking at the NFET. And we can estimate the on resistance, the NFET, the same way. If we look at the 5-volt power supply line there, look at 10 milliamps, and it looks like, I don't know, 580 millivolts there, so about 58 ohms. So somewhat smaller on resistance for the NFET than for the PFET. All right, what else could we do? We could measure it. How would we measure the on resistance of those? Well, we just look at the current and the voltage. So we need to do something that will change how much current it takes and measure the corresponding voltage. Well, let's switch back here to paper and take a look at what we do here. If we take the comparator and we take a resistor here and hook it up to a function generator, and let's say this function generator, let's say we're going to make this thing, we're going to try and measure the PFET. So we're trying to have this thing pulling high. We'll have this be plus or minus. This is trying to pull it up to high. So what we need to do is say, well, we need to have a current here that's, I don't know, 0 to 5 volts. When it's at 5 volts, so this is running with a 5-volt power supply. When this is up at 5 volts, and this is trying to drive 5 volts, there's no current through here, we're going to get nice value. But when this is down near 0 volts, it's going to be trying to pull a lot of current. And we can set this resistor to look at, well, what is the voltage here? And we could, so that's V out. And we can also look at the voltage across this resistor here and divide by the resistance to figure out the current. And if we want to be a little bit more careful, if we're not sure that this thing is going to go all the way to the power rail or something like that, we can do another one which is hooked up to the same inputs for plus and minus, but we can now look at the voltage difference between the loaded and the unloaded circuit to figure out how much the voltage has changed as a result of this load. And it's easy enough to set that up and measure it with the Analog Discovery 2. And I did that at one point for this device. And here's what I got. I got, when I'm trying to pull up the voltage, then the loaded minus the unloaded is going to be negative. And there's essentially 0 volts when I have 0 current. But as I increase the current, I increase the voltage. And I can fit a straight line to that. And in fact, I'm fitting it going through 0, so it's just fitting it as a single resistor. And I've got an estimate there that it's about 57.5 ohms for the pull-up. That's a little less than I think we estimated from the data sheet. From the data sheet, I think we estimated about 65 ohms. And similarly, for the pull-down, I did the measurement and, again, fit a straight line to it that went through 0, 0, and estimated about 44.8, 45 ohms for the pull-down. And that's, again, a little bit smaller than what we got from the data sheet. And that may be because the data sheet is usually somewhat conservative. It may be doing it at a higher temperature or something else that would affect the resistance. But the numbers are fairly close, actually, to what we would have gotten just from the data sheet. Okay, so that's ways to get R on. We had now 2 different estimates for how fast the edge would be. One is just the number that came from the data sheet. This is the rise time. This is the fall time for a small load. Or we can estimate it from the 2.2 times the RC time constant with the R on resistances that we measured just from DC measurements here. There's one more way to do it, and that is to go back to the data sheet and scroll down just a little bit further to figure 16, which gives the output transition time, thing we wanted to know, versus load capacitance, the thing that basically is going to control it. And as we can see here, we've got pretty nice straight lines. And we can just, again, pick a few points on there to get a get the curve for it rather than having to always read off the data points. And since there are straight lines, we can estimate that the rise time may be 115 nanoseconds plus 130 nanoseconds per nanofarad, and the fall time there is about 45 nanoseconds plus 110 nanoseconds per nanofarad. And for small loads, when we're looking at tiny capacitances, 50 picofarads and less, the constant part of that is the important part, because you don't get very much more for the multiplying by the capacitance. When you're looking at large loads, the linear part of that, the part that depends on the capacitance, is the important part. And so if we're looking at a nanofarad or more, you can see that the slope of that line matters quite a bit. This is probably the best estimates we'll have of the transition times. And so when you've got a data sheet that provides you this is going to be a better way to get the estimates than using just the R on or R off. It's a little harder to measure these rise and fall times because it's hard to get adjustable load capacitances. And you can play around with it a little bit, but it's easier often to measure as we did the DC on resistance, than it is to measure the transition times. But the data sheet here turns out is pretty close to what we would have estimated from the DC values. So the slope of the line here is pretty much in agreement with what we got for the measurements or datasheet values for the on resistances. And that means that any of these methods for estimating the transition times on the comparator are going to work fairly well. And we care about those transition times because if we're using it, for instance, to drive power field effect transistors, as we'll be doing in the Class D power amp, then we want to drive those transistors fast to avoid problems with shoot-through current and stuff. So how fast we can drive it is going to be dependent on how much this rise and fall time changes with the capacitance. If it turns out the comparator can't drive the field effect transistor fast enough, then we can put in a CMOS inverter, which has got slightly larger transistors than are inside the comparator, and so lower on resistances, and so able to drive a large capacitive load quicker. And for the lab, one of the things you'll be doing is looking at driving the NFET and PFET with a comparator, this comparator, or with a comparator driving an inverter that drives the field effect transistors, and looking at the difference in how fast those transitions go. So this will give you a nice way to estimate what you expect to happen, and the measurements should, if things work nicely, confirm your calculations. And I think that's all we really need right now on comparators. There is another type of comparator which does not have rail-to-rail characteristics. It's just got the transistor down to the lower voltage, so the NFET but not the PFET. This is known as an open drain comparator. Sometimes you have open collector if it's a bipolar transistor instead of field effect transistor. But the idea is the same. You only have current to the bottom power rail and no current to the top one. And that has to be provided externally for the open collector or open drain comparators. We won't be using those in this course, but there's a discussion of them in section 33.2 of the book if you do have an application that needs them. And I think that's it for comparators.